continuity equation is a differential equation which give us conservation of charge in the semiconductor. Okay, so it gives us the conservation of charge as a differential equation. Okay. Now, so let us set up our problem. We have a block of semiconductor. So this is a semiconductor block, and we will consider a, so this is x equal to 0, and let's say this is the x-axis, and let's consider a point x, and if you take a small increment, that is x plus dx, we have a strip like this. The area of cross section is A. So this is our block of semiconductor. Okay, so now we are assuming that the current is flowing in the x direction. Okay, now the current that is entering into the strip, or the, let's focus on the electrons. Okay, so let's focus on the electron current. On the electron current. Okay, so at x, the current, so we are taking the reference direction as x-axis, and we look at the current that is entering into this strip. Let's say that it is equal to J, since it is electron current, let's say it is Jn of x, and this current after a distance dx, the current that is flowing out of it, let's take it as Jn of x plus dx. Okay, you can take it as delta x also, where this is a small width in the x direction. So the current entering from the current flow direction, we are assuming that in the x direction, okay, and the current that is entering is Jn of x into the strip, and the current that is leaving is Jn of x plus dx, x plus delta x. So we are assuming it is some kind of function of x. Then charge conservation means that the total charge has to be conserved. So that is what we are trying to say. So what is the number of electron entering the strip if Jn is the current? The number of electrons entering the strip of width delta x is equal to, so number of electrons entering, say from the left, okay, into the strip of width delta x is equal to, if the current is known, we can find the number. What will be the number? This is current density, and current density, when you multiply with area, you get the total current, that is I of x, and then if you divide it by the charge, here the charge of the electron is minus q, then you will get the number of electrons entering the strip of width delta x in unit time. In unit time. So this is what we call as like the total number of electrons entering into the strip. Okay, so first I am taking the current, multiplying with A, and then divide it by the charge of the electron. That will give you the current divided by charge is basically the number per unit time, whereas current is basically charge per unit time. And if you divide it with the charge of the electron, you get the number of electron entering per unit time. Okay. Let's also look at what happens on the other side, that is at x plus delta x. So the number of electrons leaving the strip of width delta x per unit time. Okay, so this is basically happening from the right, at the boundary x plus delta x. So this will depend upon the current there, current density there, which is x plus delta x. Again, multiply with the area. We assume that the area of cross section remain the same throughout the contractor, and that divided by q. Okay, so if the number inside the strip has to increase, then what is entering should be larger than what is leaving. Okay, so the net change in the number density or net change in the concentration of the electron, therefore dou n by dou t, okay, dou n by dou t, so n is basically concentration, where what we are written down here is basically the total number. So total number per unit volume is what we call as the density. So what is entering minus what is leaving okay, what is entering minus what is leaving, that will give you the total total change in the number, but I would like to have this number per unit time, per unit volume. So I must divide this with the volume of the strip. So that is A into delta x, because I have on the left hand side n, which is concentration or the rate of change of concentration. Okay, that is what I did is this, the rate of change of concentration. What is concentration? Number per centimeter cube. The rate of change of concentration per unit time, because I am dividing it with T. So rate of change of concentration per unit time is equal to change in the number of electrons divided by change in the number of electrons per unit time, change in the number of electrons per unit time divided by the volume of the strip. Change in the number of electron inside the strip per unit time divided by the volume of the electron. So that's what I have done here. Now, is this the only way the concentration can change? Okay, so this is one way the number or the concentration inside the strip can change. But in the previous class, the last class, we have discussed about generation and recombination. So that also is a possible way of changing the concentration of electrons inside. Okay, so we have said G is what we call as the generation. So suppose due to some reason electron holes pairs are generated, then electron concentration would increase. And so therefore this is G, let's call, because we are looking at electron, let's say Gn. So Gn has a unit number per unit volume per unit second. So yeah, so you can just write you can add this Gn. So if there is electron hole pair generation, so because of that the concentration would change per unit time. So the unit of Gn, since it is compatible with what is on the LHS, so we don't need to add or multiply or divide or do anything here. This is already per unit volume per unit time, and LHS also per unit volume per unit time. And the other thing that can happen is basically the recombination. Okay, so recombination will decrease the number inside the strip, and the rate at which it is decreased, that is per unit time per unit volume, how it is decreased. So these are the only ways in which in a semiconductor you can have change in the concentration. Now let us try to simplify this further. Okay, so let me write Gn is basically generation, EHP, electron hole pair generation rate. It could be electrically injected or simply I will say it need not be even electron hole pair generation like in optical excitation. You can have other ways like injecting. Okay, so Gn is electron generation rate, and Rn is electron recombination. So whenever it is recombined, we will lose electrons. Okay, so they have unit. They have unit. So unit is number per centimeter cube second. So both of them has the same unit, which is compatible with the what is on the left side. So rate of change of concentration is basically number per centimeter cube second. Okay, so let us rewrite this expression. We have dou n by dou t is equal to, so you can cancel this a from both sides, and then yeah, you can combine all the terms. So you will have 1 by modulus q, then in bracket jn of x plus delta x minus jn of x divided by delta x. So this is what you will get from the first term due to the difference in the current entering and current leaving. So a gets cancelled off, and then q I have taken minus q, or yeah, q I am taking it outside, and minus minus cancel, so it will become jn of x plus delta x minus jn of x by delta x, then plus gn minus rn. Okay, so now in the limit we take a very small strip, so in the limit delta x tends to 0, what we have is dou n by dou t. So you see that n is now not only a function of time, it is also a function of position. That's what we are looking at here. And we are saying that its partial derivative with respect to time is 1 by q dou by partial derivative with respect to x of j j of x yeah, so you can write like this, and then plus gn minus rn. Okay, now the same thing you could have done for with respect to holes also. So then it will be like whole current entering and whole current leaving. So whole current entering will bring holes into it. The number of holes entering will be jp of x into a, but divided by plus q, because the charge of the hole is plus. So here both of these places, when you divide, instead of dividing it by minus q, you will have plus q. So there will be a net negative sign here. Otherwise it is just a change of subscript. So let me say similarly for holes we will get dou p function of x and t by dou t will be equal to 1 by q, but now there will be a minus sign here. Dou, so here it is jn and here it will be jp by dou x plus jp minus rp. So if they both are generated like the optical excitation, then of course gn and gp will be same. Okay, so these are gp and rp are whole generation and recombination rate. So this is the conservation law that we have got. So what does it say? It says that so this is continuity equation. In one form we can say there is a different form after substituting the expression for the current which we derived earlier into this expression. We will get a slightly different form, but this itself is a continuity equation. What it says is that the change of concentration at a particular point x with respect to time, if the concentration of electron is changing at a particular point in the semiconductor with respect to time, there can be multiple reasons for it. One is that the current is not constant with respect to the position. That means current is flowing more into that point, but what is leaving is less. So that way you can have a build-up of charge. If the current is not uniform, there can be building up of charge. Secondly, there can be generation at that point, and there can be recombination at that point. So all these three factors, that is the gradient of current, generation rate, recombination rate, all at this point can contribute to the change of concentration at that point. So that's what it says. So this is what is called as the continuity equation for electrons and holes. Now we can further substitute for this Jn of x and Jp of x. We know Jn of x, what is it? We have Jn drift plus Jn diffusion. Okay, so if I write that, Jn drift is q n. N is now a function of x and t. Then what else? Mu n. Mu n is the mobility of electron. You can call it as mu e also. And then electric field. Okay, electric field. So this is one way current, that is drift current. And then we have a second component, which is the diffusion component, and that is q dn, diffusion constant, into dou n by dou x. Okay, so this is the sum of drift current and diffusion current. Now if I substitute this jnx into say this is equation 1 and this is equation 2. Similarly, I can write Jp of x is equal to Jp drift plus Jp diffusion. Then it will be Qp x comma t mu p electric field plus, or no, minus. So here it will be minus q dp dou p by dou x. Again, it is a function of x and t. Okay, so we can substitute these into 1 and 2, and then we'll get a different expression. So let me rewrite. So rate of change of electron concentration with respect to time at a particular point at a particular time is equal to 1 by q dou by dou x of Jn of x, where Jn of x is q n mu n e plus q dn dou n by dou x. So this is the first term that we had, and now then plus gn minus rn plus gn minus rn. Okay, so now we have derivative of two terms, and you can cancel this these q's you can cancel, and then you have here n and e both are functions of x, so you have to apply product rule here. So mu n then e into so this is also function of x in general, e into derivative of n with respect to x plus mu into n of x okay, x and t into dou e by dou x. So this is the from the first term. Then we have plus dn. This is going to be the double derivative, dou square x comma t by dou x square plus gn minus rn. Okay, so this is a slight another way of writing the continuity equation, okay, where after we have substituted for Jn. So here we have mobility, electric field, and concentration gradient. Okay, so these are the ways in which another way of talking about the change in concentration of electron at a particular point, there could be concentration gradient in the presence of electric field, and then this one is gradient in the electric field. Okay, gradient in the electric field, and the last one is the double derivative of the concentration with respect to distance. Okay, so this is another way. Okay, so similarly we can do with respect to holes. So there we will substitute so if you do it for holes, then what will be the difference? The only difference is that we have a change in sign here. Okay, so instead of plus q you have minus q, and then in the expression also there is a minus, so we have to do it slightly carefully. 1 by q, so there is minus here, then dou by dou x, then q p mu p electric field, then minus q dp dou n by dou p by dou x plus gp minus rn. Okay, so this is going to result, again we can cancel this q's. Okay, so this is going to be equal to minus mu p then E into dou p by dou x, then we have minus minus cancelling, then plus there is one more term which is minus mu p, then p of x comma t into dou e by dou x, and then we have cancellation of the sign, and it will be dp dou square p x comma t by dou x square plus gp minus rn. Okay, so this is the continuity equation for holes. So as you can see that there are two negative signs here. Any questions till so far? Are you with me? Are you able to follow? Let me know if you have any questions. Any questions? Are you with me?
Yes, sir.
Okay. Okay, so now let's move on to an application of this equation. So what is the use of this equation? Let's try to apply it in a particular case. So now let's consider a case in which we have a semiconductor in which is very long, okay, very long semiconductor. in principle it will be finite, but let's assume that it is considerably long, especially in comparison with some of the length scales that will come out of the analysis. And what we are going to do is that we are going to illuminate light on one side, like we saw yesterday. So if you illuminate light on this side, then there is going to be generation of carriers in this side. So remember what we did yesterday. Um, so we had a situation where when we switch on the light, there will be a transient, and then that transient will go to a steady state wherein the concentration of the minority carrier increases considerably. So let's take that this is n-type. So n-type semiconductor material, illuminated not everywhere but only on one side, on this edge. Okay, far away, if you look at the concentration profile after the illumination and waiting for enough time so that the equilibrium will be reached, if I draw the uh, P, the number of holes in the n-type material as a function of time. Now there is a thermal concentration due to the thermal generation and recombination. Uh, there is a level which we call as Pn0. Now because we have illuminated light, what is going to happen is that from the thermal concentration it considerably increases, and which we yesterday called as delta P of 0 wherever the light is there. So yesterday it was with respect to time. Now I am taking x is equal to 0, and this is an x-axis because I am illuminating there only. So the curve that we drew yesterday, it was with respect to time, and what I told you is basically the time domain analysis. Now today what I am doing is with respect to the position. Okay, so yesterday's case was like we are illuminating light, or sorry, so if I illuminate with respect to time t equal to 0, I start the light on. Then what I said is that there will be a transient. So initially the concentration was like this, and then with respect to time it increases, and then it reaches a steady state value. And the length scale in this time is basically we call it as tau PL, right? Tau PL is the lifetime of the holes. Okay, so there was a transient, and then it reached this value. So this delta P of 0 was, this 0 is with respect to sorry, now here I cannot put the 0. So at infinity, so when light is switched on, we have to look at delta P at infinity. Okay, so delta, let me just write it as delta P. It's not smoothly working. Okay, so this is delta P. So after if you wait for long enough time, then it will reach a steady state concentration beyond which it will not change. So initially it was P and 0, but after the light switch on, it has become. So that happens here, but I am not plotting with respect to time. I am plotting now with respect to um, so light is getting switched on, and then the concentration rises up. So now I am looking at a particular time here, at a later time after it reaches the steady state. I am showing the concentration here. So this is this side only light is there, but far away, uh, since it is a long semiconductor, we expect that the concentration would not be affected. Okay, so the concentration, we expect that it will be P and 0, but at x equal to 0 we have a rise in the concentration, so which I am showing it like this. Now how the concentration varies with respect to x, that is what we are interested to look in. So that we do not know how. Definitely one side there is higher concentration of holes, and on the other side lower concentration of holes. We would expect that diffusion will happen. So if diffusion happens, then how will the concentration varies from here to here? It can vary so many different ways. It can vary like this, it can vary like a straight line, or it can vary like this. So many ways it can vary. So we would like to find out the concentration profile of the holes with respect to position. Okay, so this was with respect to time. You should keep both separate. So let's take the equation for the diffusion, the continuity equation for holes, which we just now derived. So so continuity equation for holes says dou p comma t, but now we are focusing on the variation with respect to x. Okay, so let me suppress in the notation this time. So dou p by dou t. So the continuity equation says p is actually a function of both x and t. Okay, and this is equal to minus mu p, then mu p into electric field into dou p by dou x, then minus we have mu p of x comma t is there. I am suppressing that in the notation. Dou by dou x of electric field, and then what else? We have plus dp into double derivative, right? So dp into double derivative of that is dou square p by dou x square, and there is generation plus gp minus rp. So this is our continuity equation. Now we have to first of all check which all terms are relevant. For example, we have not applied any external electric field in this semiconductor. All that we did is introduce light. Okay, we have not applied any potential or electric field, so I claim that electric field will be 0. But another thing that we can think about is like when these holes move from left side to right side because of the concentration gradient, uh, can there be a built-in potential, and as a result can there be an electric field? So that's a very important question to consider, but the answer is again no. The reason is that when the electron hole pairs are generated, they are generated in pairs because of the light, whatever carriers are generated. So there is a minus charge and a plus charge. Together they are generated. And what happens is that since they are nearby, these holes and electrons will have some kind of attraction toward each other, though they are in different bands, but still they are charged particles. So they will have an attraction and they will move together to the right side. Okay, so when excess carriers are generated, they are generated in pairs. Okay, and when both hole and the electron concentration are increased on this side with respect to that side, so therefore both will diffuse together. Okay, and if they are both moving, the charge neutrality is maintained throughout this semiconductor, and as a result there cannot be any build-up of potential. Okay, so there cannot be any electric field also. And similarly, if there is no electric field, there is no question of change of electric field with respect to position also. So the first two terms, because of the electric field becoming zero, though there is diffusion, but there is no electric field. Earlier when we discussed about non-uniform doping, what I said is that there is a built-in potential, and we calculated the built-in potential. But that was a different case. That case we had a doping profile very different. On one side we are heavily doping, other side we are lightly doping. So from the region of heavy doping to light doping, the electrons are moving, and as a result, charge neutrality is violated, and the electric field and potential come into the scene. But here we are introducing light, and as a result, carriers are generated in pairs. So these are excess carriers, and these excess carriers are generated in pairs, and since they are nearby, for every pair that is generated, they will have some attraction, and they move together from higher concentration to lower concentration. They move together, and why they move, it is entirely a diffusion, which is a statistical phenomena, like when we derived in the expression for diffusion current, whatever we discussed, that is the reason. There will be half of the electron moving randomly to the right and half of them moving to the left, but because there is a concentration difference from one point to another point, this will result in diffusion current. Okay, but this is done without any external electric field. Also, it will not result in any net electric field because of this diffusion current, unlike the non-uniformly doped semiconductor, which would result in a built-in potential. So here what we can say is that out of this multiple terms, the terms which contain electric field will not contribute. So this term is 0, so is this term. The reason is electric field is 0. Okay, the electric field is 0. Okay, so what matters is the remaining terms. Now, as I told you, we are not interested in rate of change with respect to time. We are interested in rate of change with respect to position only. Now here both the P is actually a function of x and time, but what I am saying is that I am going to look at steady state. In steady state, when the steady state is reached, so there will be a transient, as I told you earlier. When you switch on the light, it takes a time to reach a steady state. Once it reaches the steady state, then it maintains the concentration independent of time. Okay, then it will be, so that is the time we are looking at a time not just immediately after we switch on the light. We look at a time considerably later time. Okay, say this time t1, which is much greater than tau pl. Okay, so when we look at such a time, we will see steady state response, and we are not interested in the transient part here, that we have seen yesterday separately, okay, in a different setting. So in steady state, we will have dou p by dou t equal to 0. Okay, so we are imposing that. So this is what we mean by steady state, where things don't vary with respect to time. It remains steady. Okay, so that is steady state. and which is true for after some amount of time is evolved. Okay, after the transients are gone, and this is just like what will be the voltage on the capacitor in the steady state. You study that in network theory. So similarly, here we are looking at what is the concentration at a particular point. What is the steady state value. Okay, so LHS goes to 0. So therefore, what we can say is that, so the diffusion equation, say this equation, say, so equation 3 will become 0 is equal to dp dou square p of x. So I'm dropping down t there, x square plus gp minus rp. Okay, so this is what, so we get a much simplified expression, but it is a second order differential equation, but they are, let's say, linear equation, though okay. So now similar to this, we have yesterday spoke on these terms gp and rp. So we can rearrange this equation slightly differently. Let's say take this gp and rp on the other side and rearrange it a little bit. So that is dou square. A standard way of writing differential equation is the highest order without any coefficient you have to write. So dou square p of x by dou x square, then let's keep all the other term on the other side. So that will be equal to minus gp minus rp divided by dp. Okay, so this is what we will get. Now, as I told you, gp minus rp is a thing that we discussed yesterday. So let me see. Yeah, gp minus rp. Let's see what we derived yesterday. Yeah. So this is okay. Let me see. Yeah. So here it is g minus r. Okay, so if you look at this g minus r, so this is gt minus r. Um, so what we told yesterday is that this is equal to pn0 minus pn of t by tau pl. So you can substitute this. Now, why we can substitute this is because here only thermal generation is there. Okay, here only thermal generation is there, but in our problem we have what we have is basically light illuminating the semiconductor on one side. Okay, so only on one side it is illuminated, but all the other x values we don't have any illumination of the light. So there is generation of carriers. GL is only on this side. Okay, but inside the for x not equal to 0 we don't have any illumination of light. We don't have any optical injection. So only at x equal to 0 we have optical injection, but no other place. So therefore the only generation inside the semiconductor is GT. Okay, but recombination rate will be different. It is not a thermal recombination. Why? Because there is going to be excess carriers coming, diffusing from the left side and coming into it, and therefore we can take this expression for you can take this expression, that is yeah, this one. So gt minus r of r, gt minus r we can take, which is Pn0. So this is the thermal concentration, and this is a different concentration. So but now we are not looking with respect to time, so I will write Pn0 minus Pn of x divided by tau PL. Pn of 0 minus Pn of x divided by tau PL. So let me substitute. So this is equal to, so this whatever is in the bracket I am going to give a substitution, Pn of 0 minus Pn of x divided by tau PL, and then divided by dp. Let me just again verify. Pn0 minus Pnx, yeah, Pn0 minus Pn of x divided by tau PL. So I substitute this, and then again so that is dou square P by dou x square. So this is P of, or Pn we can write, because it is n-type semiconductor. We are looking at the holes inside the n-type semiconductor. So let's put it as P in the n-type, P in n-type. Okay, so this is equal to, now if I absorb the minus sign, this is going to be equal to Pn of x minus Pn0 divided by dp and tau PL, dp tau PL. Okay, now like yesterday, this is a derivative with respect to position, and here Pn of x is there, but right hand side we have Pn of x minus Pn0. So we can manipulate and write it without any change, this as Pn of x minus Pn0, because this is a constant with respect to position. Pn0 doesn't vary, it is just entirely the situation before any optical injection. So that will remain constant with respect to x. So when you take the derivative, that goes away. That way we have so this one I will write it as square root of tau p L into dp, the whole square. Okay, and then again Pn of x minus Pn0. Okay, are you with me so far?
Yes, sir.
Okay, all right. So now so this is a second order differential equation, and it is homogeneous. Now we have made it homogeneous by some manipulation, by just adding a constant. So this is like comparable to, like since only one variable involved here, we can just treat it like an ordinary differential equation, dx square by d square y by dx square minus some say alpha square y equal to 0. So what do you think is the solution for this? What is the solution for this particular equation, this one? You must have studied this second order homogeneous linear differential equation. What is the solution for this? Anybody? You can have two solutions. Can you tell me what is the solution? Okay, if you are not familiar, I'll write it down. So it will be e raised to a into e raised to alpha y is one one solution, and another solution is a into e raised to minus alpha, sorry, not y, it will be x, alpha plus alpha x, and another solution is b into e raised to minus alpha x. Okay, we can verify this. So you substitute in any of the solution here, first derivative, what you will get, it will, 1 alpha will come out, right? So it will be a into 1 alpha will come out. If you take two derivative, I am substituting the first solution. So if you take again derivative, a is a constant, you pull it outside of the differential, and then e raised to alpha x, you take derivative two times, you will get alpha square, and then e raised to alpha x, and the other term is basically alpha square into a e raised to alpha x. So you see that they are exactly cancelling each other, and the result is 0. Similarly, if I take the second solution, then b you can pull it out, and you take a derivative with respect to x two times, so you will get minus alpha coming two times, and then into minus alpha x, then minus alpha square into b e raised to minus alpha x. So you see that these two are satisfying solution. Okay, so let us see whether we can put these both solution in our case. So therefore Pn of x minus, our variable is Pn of x minus Pn0, we are saying it could be equal to a into e raised to now what is alpha here? Alpha here is so here I have wrote alpha square, but if you look at what is alpha is what is in this bracket. Okay, so this is so let's call it by a name, minus sorry, so plus x by L LP. Okay, I will come into why I call it as LP in a while. Plus the second solution, if there are two solutions, you can write for any linear differential equation, the sum of them is also a solution. That's a general solution, e raised to minus x by LP. Now what is LP? That is square root of where LP is the square root of dp tau p. Now let's look at the dimension, and if it is turning out to be having a dimension of length, then we are justified to use a symbol that denotes length. So what is the so there is a square root, so that I will put like and dp, what is the unit of dp? Centimeter square by second, right? Yesterday we or when we derived Einstein's relation, we found that out. Mobility has a unit centimeter square divided by volt second, and so if you forget the unit of any quantity, any constants like dp or mu p, what you can do is that take the equation that contains it. Like this is like if you look at the diffusion equation, you have Jp diffusion is equal to Q here, then dp yeah, so dn, and then dn by dx. Okay, so then you know just substitute the unit of all the other things that you, because you know all of this. So unit of this one will be equal to unit of this. So unit on the left hand side is this is current, so you can write it as it's coulomb per second, then centimeter square. Okay, it's current density, coulomb per second. Coulomb per second is current, which is ampere, and divide by centimeter square per unit area. And on the other side you have coulomb, and dp I do not know, but that is what I am, or dn I do not know. And this one is what n has basically concentration. So concentration as unit number per centimeter cube, but there is one more x here, so it will be centimeter raised to 4. Okay, so coulomb will cancel, and centimeter raised to 4, if you take it to the other side, it will be centimeter square by second. So that is correct. So this way you can find out. Now tau p we already know that it is having unit s, so this will cancel, so this will be centimeter, which is the unit of length. So that's why I am taking it as LP, and after a while I will interpret what does this length stands for. So this is a characteristic length that I am after. Okay, now we got a solution. Now if you compare these two solutions, there are two solutions. One is like x plus x by LP in the exponential, and the other is minus x by LP. Now this is exponentially rising because LP is positive, so this one is exponentially rising toward plus x direction, which is practically not feasible, okay, which is impractical, because I told you far away from the left side we expect the concentration to be Pn0, but according to the first solution, it is exponentially increasing and going to infinity, which is impractical. So the only way to get rid of that is making a to 0. So which means that constant a, by this is like applying boundary condition and finding the constant. So by the first boundary condition, that far away from the semiconductor we expect Pn0, not exponential rise and going to infinity, so a has to be 0. So therefore we got Pn of x is equal to Pn0 plus b e raised to minus x by Lp. So this is our final expression. This is how things vary with respect to x, but we have one more constant to evaluate. So let's apply the another boundary condition. So boundary condition at x equal to 0, and what is that? Pn of x or Pn of 0, that's the boundary condition. So Pn of 0, what is the question? Or you have a class at 10:30?
Yes, sir.
Okay, I'm almost done. You can okay, just 2-3 minutes. Okay, so just apply the boundary condition, we are done. So Pn of 0 is equal to what? Pn0 plus b. Okay, n x equal to 0, that is. So that means therefore b is equal to Pn of 0 minus Pn0. So substituting, therefore Pn of x is equal to Pn0 plus then Pn of 0 minus Pn0 into e raised to minus x by Lp. So now if I plot this, this is a constant plus an exponentially decaying function. So if I plot this, so that's all I want to do today. Okay, so I said that I did not know how the concentration varies, but now I know how things are going to vary. The way it is going to vary is from this, it will exponentially decrease and go like this. Okay, exponential decay. And this slope, if I extend, then the place where it meets, okay, so this is what I called as LP. So that is like the characteristic length. So after few LP, this is 2 LP, then 3 LP, say roughly by 3 LP it almost reaches the steady state value, which is Pn0. far away from equilibrium. So this is what I said, Pn0 plus Pn of 0 minus Pn0 into e raised to minus x by Lp. Okay. Now this quantity is nothing but our delta P of 0, which I have drawn here. So this is same as Pn0 my Pn0. So that's it. So this is how the concentration will vary with respect to position.